So, good morning, students. Today we are going to discuss about the ratio of driving tensions for flat belt drive. So, as you can see, as we have already done in the previous lecture about the different kind of belt drive and how we can find the length of the belt drive in case of open belt system and cross belt system. After that, we have completed the derivation for power transmission of belt. For finding the power transmission in belt, we basically need the formula of power transmission is P1 minus T2 into velocity of the belt, where T1 is the tension in right side of the belt and T2 is the tension in the slack side of the belt and V is the velocity of the belt, and this velocity depends upon pi d and pi 60, where d is the diameter of the pulley and N is the RPM of the corresponding pulley. So now the further concept is how we can find out this tension in tight side and slack side. For this, we first have to find out the ratio of driving tensions for flat belt drive. For this, we are just drawing one diagram. Suppose you have a driven pulley and the belt is just entering at the driven pulley at this point A and leaving the driven pulley at point B. So here you have the tension T2, that is tension in slack side, and here you have the tension T1, that is tension in tight side. So this is our center point. Just join this center point O with this A and this B. So further, this angle is known as the angle of contact or angle of lap between the belt and pulley surface. Now, further to calculate the tensions, the ratio of the tensions in tight and tight as well as of the slack side, we firstly consider one small portion here PQ, and suppose at P there is the tension T, that is tension towards the slack side, and similarly here we have the tension T plus delta T, that is tension towards the tight side, and this angle made by the PQ at the center of the pulley is delta theta. Further, we have the different force component here. Towards the horizontal side, we have the normal direction. Suppose the belt is moving in the clockwise direction, so there would be one component of force normal to the horizontal component, that is F, and it is equal to mu R M. Further, for the simplification point of view, we divide this triangle as like this. So this is point Q, this is point P, and at point P we have the tension T. Consider here we have the normal direction RM. You can just extend this point. Here we have the tension T plus delta T. Now draw one perpendicular to the normal direction from this point. So it is the vertical component of this tension at point T, T. And similarly here We draw the perpendicular. So this is the vertical component and it is in downward direction vertical component of t plus delta t. Now this angle is delta theta by 2. Similarly, this angle is delta theta by 2. Further, we are going to solve the equation. Now, firstly, here one more force, that is the force, frictional force, vertical component, F equal to mu R N. Now, as we know, the algebraic sum of forces in horizontal and vertical direction will be zero. So, firstly, we will resolve the forces in horizontal direction. Horizontal direction. So horizontal direction, the first force is Rn, this direction. Now the component of this force T plus delta T in horizontal direction will be T plus delta T multiplied by sine delta theta by 2. Similarly, the component of this T in horizontal direction will be T sine delta theta by 2. And almost the component of this in vertical direction will be t cos delta theta by 2, and in this direction t plus delta t cos delta theta by 2. So you can see here Rn is equal to t plus delta t sine delta theta by 2. Similarly, here we have plus t sine delta theta by 2. Now you can see here that value of delta theta is very small. So if sine approaches to very small angle, it has a very negligible value. So we can write sine delta theta by 2 is approximately equal to delta theta by 2, because the value of angle is very small. Further, Rn is equal to, when we open the equation, T sine delta theta by 2 means d delta theta by 2 plus delta t into delta theta by 2 plus t delta theta by 2. Now, further, these both quantities are very small in nature. So, when we multiply them, they further results into very small quantities. So, we can neglect this value. So, we ultimately got 2t delta theta by 2 and t delta theta, because 2 get cancelled out. So this is our first equation in which the normal direction is equal to t delta theta. So the next thing is we have to divide the forces now in vertical direction. So in vertical direction we have the force, first force is this F, then we have this T cos delta theta by 2, that is the vertical component of this tension at point P, and then here we have the component T plus delta T into cos delta theta by 2. So we can just write forces in vertical directions. So F is equal to T plus delta T cos delta theta by 2 minus T cos delta theta by 2. When you will open the equations, then we get cancelled out T cos delta theta by 2 by T cos delta theta by 2. Ultimately, we get cos delta theta by 2. Now, as we further know, the value of delta theta is very small, so cos delta theta by 2 is approximately equal to 1. We can assume as cos 0 is equal to 1. So, F is equal to further coefficient of friction multiplied by normal reaction. So, it is value become delta T because this value is equal to 1. So, this is further Rn is equal to delta T by mu. This is equation number 2. Now, when you equate the equation 1 and 2, on left hand side we have the Rn and on the right hand side we have two different values. So, both right hand side will also be equal. So, again, I'm just erasing the portion for making the space, or otherwise I can add some blank page, insert a blank page. So, we have the another page. So, we get the value further Rn is equal to T delta theta, and here we have the delta T by mu. Now we can just write delta T by T is equal to mu delta theta. Now we will integrate both sides. So the value of tension rise from T2 to T1. T1 is the maximum value, it will come here. So and the value of theta rise from 0 to theta. So when we solve this equation, 1 by T delta T, it will become log of T, T1, T2, and it becomes theta 0 to theta. When you put the value here, it is a natural log T1 minus T2 mu theta minus 0. So and further it is equal to T1 by T2 mu theta, and you can also write it as T1 over T2 log, here comes e raised to power mu theta. So this is the ratio of driving tension in case of the flat bed valve. In some of the books, instead of this log, they use 2.32 log and T1 by T2 mu theta. So this equation you can also use. So this is a very important equation for finding the ratio of driving tension of tight and slack side. So in the tomorrow lecture, we will cover the numericals related to the ratio of driving tension, and we will find out the power transmission in case of flat belt.